Start this. All right. Let's do what we do. That's not us. Exponential decay. Today, we're starting chapter 7. And if you remember, we're only doing chapter 7, chapter 8. We're going to duck into chapter 9 just briefly, but hardly even counts. So we're in the home stretch here. Chapter 7 is on inference for numerical data. Now, I really didn't like the slides, so I pulled in some old slides, which are really old, so I'll kind of rejig them as I go. But it's one of those things that I don't remember that I should fix until I'm at this point next term. Thinking, oh, I should have fixed that. Oh, well. So, one sample mean with a t-distribution. We've been using the t-table already, so we know how it works, but now we're going to use the whole kit and caboodle. One thing that I almost forgot to mention is we're going to do one sample mean today, and then I will post a video that I recorded a long time ago, but it's going to be on 2 sample means. Okay, and so if we move into 2 samples, and so for Tuesday, Tuesday, a video will be posted. A video, on 2 sample means will be posted, which means no lecture, because it's the Tuesday after the long weekend. And if I can pull it off, it'll align perfectly with this video, and I could not be more pleased because it's 1 hour and 52 minutes long. But I can't decide if I make you watch the whole thing. I know you guys are doing sneaky stuff like watching it at time and a half and stuff, but so you can do it. But maybe I'll just make you watch half or something. Okay. What I'm leaning towards is making you watch the whole thing, and then we review the whole thing on the Thursday next week. It's time to decide on that, I guess, but I haven't decided yet. Okay. So far, we have developed techniques for inference, things like confidence intervals and hypothesis testing. That's what we mean by inference, right? We're trying to infer something about the whole population. And so far, we've only talked about categorical data where we have proportions. So we're analyzing proportions, 1 sample proportion, 2 sample proportion. If we have 3 or more, we can use chi-squared. And then if we have 2 variables of different categorical variables, I can use a chi-squared test of independence, which is what we finished last day. Now we're going to introduce inference for numerical data. Numerical data, if we think back to the very beginning of the course, feels like just yesterday, right? The question that we asked ourselves was to determine if it was a numerical variable, right? We ask, does it make sense to talk about the average? To talk about the average, right? That was kind of our deciding factor. If it makes sense to talk about the average, then we call it a numerical variable. Now, if we have a numerical variable, we are going to analyze the mean, x bar. but we're really trying to learn about the population mean, mu. And so on your formula sheet, let's go there, if I can grab it. We finished chi-squareds last day, and so now we're in the one sample mean section. It's new and kind of foreign looking just because we haven't dealt with X bars yet. But what happens is we're going to have paired data and then two sample means, and then we're into regression. And then that's it. It's always kind of exciting for me when we can see the end. Not because I want it to be over, but because I think it's really exciting to show you all the things that you've learned so far. Okay. Applying all the concepts that we have from before, from proportions, right? Then this, we know that this part is theoretical and we can still ignore it. This is the sampling distribution of X bar. And so this is the sampling distribution of X bar. So what does that mean? Well, X bar follows a normal distribution centered on mu with a standard error of sigma over root n. Might be nice to recall mu is the population mean. Oops. And sigma is the population standard deviation. And n, of course, is the sample size. Which means that the standard error of X bar is sigma over root n. Okay, so the spread of X bar is sigma over root n. Okay. If we think about a confidence interval, right? The general layout of a confidence interval is the point estimate plus minus, and then we're used to seeing a Z star, but now it's turned into a T star. And we'll kind of see that they're basically the same, basically. And we don't have sigma anymore, but this S over root n is the standard error of X bar, so the standard error of the point estimate. And so we have that same general layout. So a general confidence interval has a point estimate plus minus, I'll call it a critical value. Critical value. It used to be Z star, but now it's going to be a T star. But again, it just determines the width of your interval. And then times the standard error of the point estimate. For your hypothesis test and your general test statistic, is going to be your point estimate. Oops. Oh, eraser. Your point estimate minus your hypothesized value. How far is it from the hypothesized value, taking into account the standard error of the point estimate? Once we know the spread, right, we take that into account, and then any test statistic has that format, right? Which means that, okay, if I have the point estimate and I have the standard error of the point estimate, and I know it follows a normal distribution, then that's a lot of knowledge that I have. Now, the only problem is that it follows the normal distribution if I know sigma. But I don't know sigma because sigma is the population standard deviation. And if I knew what the population looked like, would I need to collect a sample to try to figure out what the population looked like? Probably not. I could just look at the population and use that instead. So that's unlikely. So then when we use S over root n as our best guess, then we kind of we move away from the normal distribution because it's trying to approximate the shape of all your X bars. And then, but it's also having to account for the standard deviation being from the sample as well. So it becomes this kind of scenario where you have to, rub your stomach and pat your head at the same time, right? Because you've got your X bars and your S's both from the sample, right? And they both contribute uncertainty. For us, that's not something to keep track of, but it is why we have to use the T distribution instead of the Z distribution. Okay? And so for means, we're going to use the T distribution, which behaves very similarly to the Z distribution, with the exception of now we have degrees of freedom. Okay? We've seen this concept before of degrees of freedom. So the T distribution depends on the degrees of freedom. We've seen the degrees of freedom in the chi-squared distribution, right? The shape of the chi-squared depends on how many degrees of freedom you have. And same thing with the T distribution. It's just, so now depends on your sample size minus 1. And so what happens if you have a T distribution, and I think I have blah, 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 blah. I'll come back there. A T distribution, let me just grab this. Copy. Because I do want to talk about the assumptions, of course. But I'm going to put it down. Put her there. So the normal distribution that feel like I'll just go mute everyone just in case. So the normal distribution is the Z distribution. And the blue line or the solid line is the T distribution. Now the T distribution, some key characteristics here are that I have more area in the tails, right? And that means that it's kind of squished down. The total area is still 1 under the curve, and the area under the curve is still a probability. But what happens is if you have small sample sizes, then the tails kind of lift up and say, hey, this is a really small sample size. I don't know what's extreme or not, right? The probability of these more extreme things happening is large, right? But as you increase your sample size, what's going to happen is those tails are going to push down and it's going to approach the normal distribution, right? And so here, notice, and maybe I'll say, notice T has more area in the tail. So, and of course the area is the probability. So it just allows for more observations further into the tails. Okay. But as the degrees of freedom increases, which means that, okay, if the degrees of freedom is n minus 1, then really it's just as your sample size is increasing, right? Or n is increasing, the t distribution approaches the z distribution. The t distribution approaches the z distribution. I will say the reason for it, but it doesn't matter to us in applied situations, but the reason for it is because as you take up more and more of your population, so as you increase your sample size, you're getting closer and closer to the population size. And so that means that your standard deviation, your sample standard deviation is getting closer and closer to your population standard deviation, which follows a z distribution. That's not for us, but that's what's going on behind the scenes. Okay. In terms of our conditions, we have to make sure the observations are independent. We can do that again just by randomly sampling. Random sampling. And as long as the population is not extremely skewed, even though as long as you have a large enough sample, you can even draw from a skewed distribution and analyze the means still. Okay, but then you would need to increase your sample size. But if as long as it's not extremely skewed, then a large sample, we're going to use a sample size larger than 30. Okay, would ensure that the sampling distribution is nearly normal, and S over root n is a reliable estimate of the standard error. So in terms of our conditions for means, they're a lot easier, right, than for proportions, for example, right? We had to make sure we had a random sample, that it was less than 10% of the population, success failures had to be greater than 10, that kind of thing. Now our conditions are going to simplify to this. We still have the independence condition, if you like that breakdown. Independence. Randomly sampled ensures that we have independence. And then our normality condition. So we still have the same breakdown of the conditions, it's just how we check them changes and is simplified in a big way. Population is not extremely skewed. And greater than, you know what? I'm going to change it. Population is approximately normal. Or if it's not approximately normal, so how the question would usually go is you would say, okay, if I have a small sample size, which happens, then I have to assume that it's approximately normal. It came from a normal distribution. Or it would say it came from a normal distribution. If it doesn't, then you better check that your sample size is big enough, right? Or n is greater than or equal to 30. So as long as your sample size is larger than 30, then you don't need to have drawn from a normal distribution. You can draw from any distribution. And I think that's pretty cool. So way easier conditions than we're used to seeing. Okay. And do we need to talk more about the conditions? Fine. The central limit theorem applies for means as well, right? We saw it for proportions. In fact, you did a lot of work with one sample proportions in that Excel lab, right? Where you had to find the mean of all the sample proportions, right? And you found that they follow a normal distribution. And so the central limit theorem, you can do the same thing for sample means. But now you're finding the mean of means and it gets kind of boggy. But the sampling distribution is going to be nearly normal as long as the population distribution is nearly normal. Like we were saying, okay, that's not always the case where I have a nearly normal population. And so if you're dealing with a small sample, right, then you want to think about, okay, do I expect this distribution to be at least symmetric, right? Maybe unimodal and symmetric, right? You don't expect there to be a ton of outliers, right? You expect things to be centered on some number and more common around that number, and then kind of decrease in popularity as you move further out. I'm going to skip this condition. So here's a summary of the conditions. It has to be a random sample, so that's the independence condition, and then the normality. And we have that sample size condition. The population must be much larger than the sample, say at least 20 times as large. That's the same as the n less than 10% condition. And so I'm going to skip this condition. I used to do it, but now I don't. Okay. The t distribution. The t distribution is always centered at 0, just like z. And it is bell-shaped, but the tails are thicker than the normal distributions. Like we said, okay, then it's allowing for higher probabilities of those extreme values. It quickly approaches the z, though. Okay? And so observations are more likely to fall beyond 2 standard deviations from the mean than under the normal distribution. So now our go-to of 2 standard errors, or a z of plus minus 2, we're going to have to bump it out just a little bit if we're using t's, but not too bad. Okay. Here's the one that I grabbed before, but I want to talk about the degrees of freedom. Okay. So the t distribution has thicker tails for small sample sizes, and then the tails get thinner as the sample size increases. So like I said, if you have a small sample size, then and you should see this too. I'll start my video. I can't see myself though, so I don't know. But can you see me? I don't know. So as your sample size increases, then it's going to smush up and kind of close the tails. It doesn't make sense. I'm hoping it's in the video because there's a lot of arm flapping going on. And the tails smush down onto the x-axis. That was my best attempt. So the degrees of freedom is how we're going to communicate, okay, what will be the shape of the t distribution. And so as your degrees of freedom increase, so the solid line, so this top line is the normal distribution, which is our z. And then as the lines fade, our degrees of freedom are decreasing, which means that, okay, if I have 10 degrees of freedom, then n must be what? 11, right? N minus 1 is the degrees of freedom. So n must be 11, n must be 6, n must be 3, n must be 2. A sample size of 2, are you kidding me? You don't want to do that. In fact, I think even 6 is a little bit dicey. Okay. But if we compare these, right, notice that, okay, for 1 degree of freedom, that's kind of as lifted off in the tails as we can get, right? It has the most area in the tails because it's kind of lifted off like that. It still looks relatively familiar, though. It's not a flat line, right? It still has that kind of unimodal symmetric shape. So even at a sample size of 2, it would still behave like we think it does. So then we quickly move up. Okay, if I have a sample size of 3 or 2 degrees of freedom, right, then the tails are kind of smushed more down on the axis. 5 degrees of freedom, it's even closer, right? Even at 10 degrees of freedom, so a sample size of 11, which I think we can all agree is really small still, okay? It behaves basically the same as a Z, right? So as long as your sample size is, we said more than 30, then we can go ahead and just assume it behaves like the Z distribution. We're going to get picky and we're going to use t values in the t table instead of the Z values. But, okay, so here I talk about the t table, but I changed things up this year and I made you use the t table always. So I'm going to bring it in here. Copy. And I guess I paste. Didn't need this page there. So this is the table that we've been working with always. And it is called the t table. I've tried not to call it that because we've only used it for the Z star line so far. So we've been working down here and we know how this thing behaves, how Z behaves from this Z star line, right? If I need to make a confidence interval, for example, then a 95% confidence interval, then I scroll down, and I find my critical value is 1.96, right? Now we're going to do the exact same thing, but we need the degrees of freedom. That looks kind of weird. Just didn't, this dark highlighter, fine. I won't highlight this anymore. I'll just highlight the new things. Whee. So we've got the degrees of freedom. The degrees of freedom is n minus 1, which is on your formula sheet, right? And as we move into other numerical data type questions, right, 2 sample means, we need to figure out how do I find the degrees of freedom, and then I can calculate a t, and as long as I have a t, I know how it behaves. Just like if I was able to find a z, then I'm back on familiar ground, right? Notice, some rules about the degrees of freedom is it stops going up by 1 after 30. Now, what I want to make a note of here is if the degrees of freedom that you have is not listed exactly, you have to round down. Okay. And so the reason for that is if you're rounding up for your degrees of freedom, then you're saying that you have a bigger sample size than you actually do. And that's bad, right? Because a bigger sample size gives you more certainty. And so to claim that you have a lot of certainty when you actually don't is really, really bad. So important. If the exact degrees of freedom is not on the table, we need to round down to the closest degrees of freedom. We need to round down to the closest degrees of freedom. So for example, if the degrees of freedom is, I don't know, 78, you're so close to 80, but you're going to have to use 60, right? Because if you went to 80, you're saying you have a sample size of 81, when in fact you only have a sample size of 79. It's not a huge deal, but it's just the convention. And it's the principle. You'd be claiming to have a larger sample size than you actually do. So use degrees of freedom equal to 60. Even if degrees of freedom is 900, you're choosing between 100 and 1,000. Well, you're not quite at 1,000. So then you have to use 100. Use degrees of freedom equal to 100 in the table. If you're using software, of course, you can use the exact degrees of freedom, right? That's cool. But if you're using the table, you have to use, you have to round down. Okay. What if we compare these? Let's compare the Z star line that we know and love. Let's compare it to degrees of freedom of 1,000. So a sample size of 1,001. These are basically the same, right? I'm not seeing a huge difference here, right? It's as we move further out into the tail, they get a little bit more different. But even if we compare, let me just temporarily grab this Z star line, copy, and I'll even compare it to paste image. I have to say out loud what I'm doing. Hey. Okay, too big still. Hard to compare. But if we just temporarily compare 20 degrees of freedom and Z star, they're still relatively similar, right? It's just that 20 degrees of freedom, we expect them to be a little bit further out into the tails, right? Because we have more room in the tails. And these cutoffs are determined by how much area is in the tails, right? And so I expect to be a little bit further out in at 20 degrees of freedom versus Z star, but they're essentially the same, right? Gets a little bit different as we head further out into the tails, those really, really small areas. But in general, it all behaves the same way. So all those skills that you have from Z, they translate to T's. Yeah. So like I said, you know how to find your critical value for your confidence interval, for example, right? Because what are you going to do? Once you have your degrees of freedom, n-1, your sample size doesn't change. So once you have your degrees of freedom, you're stuck on that line and you ignore everything else. Just like we ignored everything else when we were on the Z star line. Right now, we just shift our focus to whatever degrees of freedom we have. So then, if you want a 95% confidence interval, and we have, let's say, 15 degrees of freedom, then your T star would be 2.131 in your confidence interval. Right? If in your hypothesis test, you calculate your T, and then you have, let's say, 15 degrees of freedom here, then you try to place your T, where does it fall? Right, T is also symmetric about 0, and so you drop the negative, and you try to figure out where it is on this table, and then takes a little bit more work. I use my fingers on the table, and then you're going to trace down, and you're going to be able to find your one-sided or your two-sided P's the same way that we have been doing. So, any questions so far?
How many degrees of freedom do you need for it to become Z?
Infinity. At the population size, you're at Z. Yeah. So yeah, technically infinity, or whatever your population size is, then you have all the information. Is there another question? No?
This 30 kind of like 30 pretty close.
Yeah. So here, if you compare kind of the 30 line, it's still a little bit wonky out here, way out, but these areas are super, super small, right? And so it still kind of behaves the same way that we expect it to, right? All right. I think I have an example, or did I really drag it out here? Blah, 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 blah. This is not true for us. We have not been using the Z table. I forgot to change that. That's okay. Time to bring some jokes, I think. Don't know what a p-value is, and I'm too afraid to ask. That's fair. P-values are these like things at this point in the course. I'm happy if you recognize that, okay, p-values seem to be an important thing, but I don't really know what they are yet. That's okay, I'm happy with that level of knowledge. And so just keep at it, and eventually it will click, okay? And so just in case it's feeling like, oh man, I cannot ask her what a p-value is at this point. You can, it's okay. I actually don't expect you to know what the p-value is yet, right? It's the probability of seeing something as extreme or more extreme than what you saw, assuming the null hypothesis is true, but that's kind of hard. How about the p-value? Oops. I'll write it here, but just because I write the definition doesn't mean that I expect you to kind of internalize that, but I should write it out because I talked about it. So the p-value is the probability of seeing something as extreme or more extreme, more extreme than what you saw, implied here in your sample, assuming the null hypothesis is true, assuming the null hypothesis is true. If we think about probabilities as areas under the curve, right, we're still going to draw the same kind of generic shape because we saw that it doesn't really matter what the degrees of freedom are. They still have this same shape. Okay? And it's still centered on 0. This is for the t distribution, but also for the z. Yeah. And so if we saw something out here, right, if we saw that t was 2.340, I don't know, just making something up. That's after you've done the calculation, right? You took your x bar, you subtracted from your null hypothesis and or your hypothesized value, took into account the spread, and then you found that your mean, your observed sample mean, was 2.34 standard errors away from 0. So here, the probability is the area in the tail. This is the one-sided p-value. Right? As extreme or more extreme makes the area in the tail. We're only going to have approximations for that area, right, from the table, but then we can use software and we can find the exact p-value, right? There is an area, but from the table, we just get a range for the area, which is fine. That works too. And then if you have a two-sided test, right? So if you have not equal to and your alternative hypothesis, then you replicate it down in the other end and say, okay, I would be just as concerned if I saw the same thing on the other side, right? And so that's where the one-sided, two-sided p-values come from. But your table just gives you both, right? And so it's just done the multiplying by 2 for you. So I'm just going to leave it like that because I think it's nice to see just the one-sided p-value, and then you would multiply it by 2 if you wanted the two-sided p-value. Okay. There. That's the p-value. No, I still don't expect you to understand the p-value. It's okay. Just know that it's very important and that you should work on it. I'm happy with that. I want to start with an example of hypothesis testing because, as we know, those steps are way more rigorous than confidence intervals. Okay, and so I've got this example here, and we're going to work through it. Okay. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. So as you can imagine, there are a lot of these measurements happening all around the valley where they have to make sure that the water is actually livable for all our creatures. And so a researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Okay? If they're randomly chosen, then we can assume that these 15 locations are representative of the entire stream, so that's nice. And we get the results in milligrams per liter. Now, I usually ignore units because, man, they're so annoying. But don't tell your chemistry teacher that. They don't like it when I say that. Units. Physics, too, they want units. Me, nah. So we've got 15 locations, right? And we've got these these numerical measurements, right? And so now I can calculate the mean of this sample, right? And I can calculate the standard deviation of the sample. I will not make you calculate the standard deviation. I'm going to give it to you. And that's kind of a go-to way to confirm that you have a means type of question, right? Because now we're going to have to decide, okay, do I have a proportion question or do I have a means type of question? Because that's going to kind of determine, okay, Z or T, and kind of be a decision point. So if I give you the standard deviation, then it's going to be a means problem because that's the only way I can get the standard deviation. So the mean and the standard deviation of the sample, I find X bar is 4.77 and S is 0.94. Here's the pickle. A dissolved oxygen level below 5 puts aquatic life at risk. That sounds bad, right? So we don't want that. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Okay, here we go. Let's check our conditions just briefly, because they are brief. The locations were randomly sampled, so that's good. The normality condition said, okay, I either have to pull from a normal distribution or my sample size has to be greater than 30. So when I look at my sample size, I only have 15, N is 15. So what do I have to assume then? I have to assume that the dissolved oxygen levels in the entire stream are approximately normal, right? So here, since N is 15, which is less than 30, we must assume dissolved oxygen levels are approximately normal or approximately normally distributed. I've been calling them the conditions, but really we're stating our assumptions, right? Or assumptions. Check the assumptions. Either way. If I'm assuming it's approximately normal, then I'm good to go. So now, step 1, state the hypotheses. Let's go back to your formula sheet. Where is it? We're doing a hypothesis test for mu, so I'm using my sample mean, but I'm really trying to learn about the population mean, right? And so my null hypothesis, this looks familiar, right? My null hypothesis is that mu is equal to mu naught. So some hypothesized value from the question. We've seen that before with one sample proportions. And hopefully I don't lose it. It's a secret. The null hypothesis is going to be, how does mu compare to 5, right? Because from here, this means that mu naught is 5. The value I want to compare, the value I want to compare X bar to. Right? I have my sample mean and I want to compare it to 5. And so that's what makes my mu naught 5. So mu is equal to 5. The alternative hypothesis has to be about mu, and it has to be about 5. The only thing that changes is the sign here. So mu and 5, and a dissolved oxygen level below 5. So I'm not concerned if it's significantly higher than 5, although 4.77 is less than 5, but we're concerned that it's significantly less than 5. So here, I want to know if it's less than 5. This is one of those scenarios where we're actually really hoping that I don't have enough evidence to reject H naught, because that would be really bad, right? This is when all the fish die. And so I'm hoping that everything's just kind of hanging out around 5 and it's all good. I am going to make a note here. This means I have a one-sided test, right? I'm only concerned about anything less than 5. And so this is a one-sided test. We don't need that until we need to find the p-value, right? So we need a one-sided p-value. Okay. Step 2. Calculate the test statistic. Do the test is usually how I do. The test statistic is a t now. All right, and so from here, I want to calculate this t. How far is our sample mean from 5 if I take into account the spread? So t is X bar minus mu naught divided by S divided by root n. X bar was 4.77. S was, I want to say 0.9, I was going to say 0.97, but 0.94. N is 15, and we just said mu naught is 5. Matter of plug and chug at this point. 4.77 minus 5, how far is it from 5 if the spread is 0.94 divided by the root of 15? I like to do the 0.94 divided by the root of 15 first, and then I don't have to worry about it. If I can punch things in properly. And then 4.77 minus 5 divided by that guy, I get a t of negative 0.9476448613. That's a relief. Why? Because I didn't want to reject H naught. So now I'm saying, okay, it's only 0.95-ish. Standard errors below the value of 5. That's not very far, right? And so in terms of, and I guess next step is find the p-value. Step 3, find the p-value. If we draw this thing, move it over. T is centered on 0, and we found a t of negative 0.948, let's say. Which means, bless you, the p-value is the probability of seeing something as extreme or more extreme, which is this area here. This is the one-sided p-value. The only new thing is that, okay, I need to find my degrees of freedom first, right? So my degrees of freedom is n minus 1, which means, and I don't like to do calculations across the page, but these are just so little. 15 minus 1, I have 14 degrees of freedom. Huh? So what I'm going to do is we can set up, right? As long as we use 14 degrees of freedom, then you can check on your table and you have a line for 14 degrees of freedom. So that's cool. And because it's really easy to kind of go cross-eyed looking at this thing, usually what I do is I recommend just, you can use the page, use it against itself as a straight edge, and you can kind of fold it up and then you're not jumping around, right? Because it is really hard. But the setup is the same as for Z's. You start with your t in absolute value brackets, 0.94, I'll do 8, is somewhere between two values. Now, let's see what's less annoying. Probably scrolling is kind of annoying. So we have 14 degrees of freedom. If I try to place 0.9 something on here, it's somewhere between 0.868 and 1.076. We do the same thing that we were doing. This is a nice time to check in and make sure that this value is actually between the two values that you tell me. Even if, you know, you're kind of in a blinded state in the test, and for some reason you tell me that it's between 0.6 and 0.8, that's not true, right? But as long as you followed through with that, I would, you know, take marks off here, but as long as you follow through, you're okay. Because those things happen, and that's not really what's important here. But what does that mean? That translates onto our little graph here, which you don't need to do, but I think it's nice. Negative 1.076 and negative 0.868. The table tells me that that area is somewhere between two values, right? So now if we trace down, oh, I shouldn't. Scroll all the way up. Okay. So I was between these two values. And I find that my this is when I need to decide, do I have a one-sided, or do I need a one-sided P or two-sided P? We said we had a one-sided test because I'm only concerned with values less than 5, right? And so I have a one-sided P and it's somewhere between 0.15 and 0.2. So here, this was at 0.15 and this was at 0.20. So then the one-sided P is between 0.15 and 0.20. Nice. If you prefer, what else could you have done? If you prefer the critical value approach, right? Like we used for chi-squareds. Okay, any chi-squared bigger than this, then I reject H naught. The goal is, can I reject H naught or not, right? And so then what would that look like? You could use it here. You don't have to use the p-value approach, but what it would look like would be, we were told to use an alpha level of 0.05. So then what we could do is we could say, okay, I have a one-sided test. I'm going to force that area to be 0.05. So then here, if I trace up to 14 degrees of freedom, what this tells me is, okay, I need to have an absolute value of t larger than 1.761, right? So, or less than negative 1.761, more into the tails than that. And then you can use that instead as your argument. We're going to use the p-value approach. And while I'm here, I better remove these because that'll be confusing later on, I think. But you're welcome to use the critical value approach if you want. Your conclusion will be the same, right? Either you've passed that threshold, therefore you can reject H naught, or your p-value is less than the alpha level, therefore you can reject H naught. They're the same. But step 4 is your conclusion. This is what I was holding on to that whole time, because I realized I forgot to put it in the notes when I said I was going to. There he is. If the P is low, then the null hypothesis must go. There you go. Just to help you remember. In case the definition of the p-value doesn't help you that much yet. Okay. So our p-value is somewhere between 0.15 and 0.2, which is not low compared to 0.05, right? We were told to use 0.05. And so then I don't have enough evidence to reject H naught. So we say, since the one-sided p-value is between 0.15 and 0.20, it is not less than alpha equal to 0.05. Should make this a prettier alpha. Oh, still got a little Irish on it. There. Which means we do not have enough evidence to reject H naught. Notice how I'm using the mirror, right? So I'm not going to say it's greater than 0.05. I just say it is not less than 0.05, which means we do not have enough evidence to reject H naught. Which means we do not have enough evidence to reject H naught. What does that mean? That means that the dissolved oxygen level, the mean dissolved oxygen level, let's go back to the question, because at this point, we just reword the question as an answer. Is there evidence that the aquatic life is at risk? No, it is not, right? Because the dissolved oxygen level is not significantly less than 5. Therefore, the aquatic life is not at risk since the mean dissolved oxygen level is not significantly less than 5 milligrams per liter. I'm searching my stickers. I've got this whale, but I have fish somewhere. There. They're all happy. Ta-da! We did it. All the same steps. We just tweak what our hypothesis is about. Now I'm hypothesizing about the population mean, right? And I tweak my test statistic because now it's a T. And then that means I use the T distribution in the T table to find my p-value. But once I have my p-value, the conclusion and the format of the conclusion stays the same. Remember, the conclusion is always 3 marks. So first, you have to compare your p-value to your alpha level. Right. 1. Compare the p-value to the alpha level. Then, what does that mean in terms of H naught? Remember, we did all our testing assuming that mu was equal to 5, which was my null hypothesis. So we did all our testing assuming the null hypothesis is true. So that means that we have to state our conclusion in terms of whether that's likely or unlikely. So then this is your conclusion in terms of H naught. That's important. And arguably the most important is, what does that mean in terms of the question? So your conclusion in terms of the question, right? Answer the question. That's the one people love to forget. It feels like you did so much work to get there. We can build a confidence interval for the dissolved oxygen level. What would we find? We would find that 5 should be in there somewhere because we didn't reject H naught, which means it's a perfectly reasonable value for the dissolved oxygen level. So if we built a confidence interval, we would expect mu equal to 5 to be in the interval, right? Since we failed to reject H naught. To be in the interval since we failed to reject H naught. You can build it. Usually we don't go ahead with confidence intervals if I don't reject H naught. It's more if I've rejected H naught, then I would ask a follow-up. Okay, well, then what is a reasonable value for mu? Here, 5 is a reasonable value for mu. And so kind of case closed. Let's do an example of a confidence interval. And I'm guessing that's been changed because that'd be terrible if I hadn't. Yeah. So business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB. And included in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. A study is based on a random sample of 75 reports. Okay. So here I've got N is 75. I like that it was randomly sampled. What does that tell me? It tells me that these reports are representative of all reports from the current year. The average debt, which is the liabilities minus the assets, is $92,172, with a standard deviation of $111,538. We're ignoring the fact that the standard deviation is larger than the mean. Usually that's bad, but we're ignoring that. Construct a 95% confidence interval for the average debt of these companies at the time of filing. Okay. So the average debt of the sample tells me that this must be X bar, and this must be S, the sample standard deviation. It's not obvious that those are the samples, but on the test, I usually try to make a point of saying, okay, the average of that group or the average was found to be, the average of the sample was this. Okay, here it's kind of buried a little bit. A study is based on the random sample from the current year. The average debt was this and the standard deviation of this. But you can assume that those are the sample mean and standard deviation. I want to construct a 95% confidence interval for the average debt of these companies at the time of filing. So I need my confidence interval formula, or maybe you don't. You just know it, right? Looking at what we have, I have X bar. I don't have T star, but I have a pretty good idea of how to find it. I have S and I have N. So I have all these components. I just need to find T star more explicitly. And so using the T table with degrees of freedom equal to N minus 1, and N was 75 minus 1, which is 74. If I go to, now that I've pasted my Snoop, then I can copy from here. If I try to find 74, I'm choosing between 60 and 80, but remember we have to go to 60 because if you go to 80, you're saying you have a bigger sample size than you actually do. And that is not good. We want to find, let me just temporarily put this up top here. Can I do that? And then copy, delete. Sneaky, sneaky. So usually what I do in my written work is if I don't find the degrees of freedom that I want, right? The degrees of freedom is 74, technically. So if I use software, I would use 74. Yeah. But using degrees of freedom equal to 60 in the table. All right. Not 80. But from here, that's fine. I wanted a 95% confidence interval. Look at this beauty. It's exactly 2. It's the only one on there. T star is 2.000, which we were using 2 as a rough guide. And then we found that, okay, we should probably use 1.96 for Z. So this is kind of the rare instance where we actually do use 2. So now I have my T star and I'm ready to say X bar plus minus T star. I will make a note here. This subscript n-1 is really just saying T at n-1 degrees of freedom, right? And so here, this is just saying T star at n-1 degrees of freedom. Or you can just write T star if you want. And just remember that you need n-1 degrees of freedom. So T star times S over root N. Grabbing all the components I need, 92,172. Plus minus 2.000 times S, which was 111,538. Divided by the root. Now, here's the pickle. Throws people off because we use 60 as our degrees of freedom, but that has nothing to do with our sample size, right? Our sample size is still 75. Okay? So you want to keep track of those. 75. I'll highlight that because N is still N, but our degrees of freedom, what we're using is 60. Okay. Let's find the standard error. So this is the standard error in the brackets, right? Once I multiply it by 2, it's still the margin of error, right? And let's see here, 111,538 divided by the square root of 75. And I'm just going to multiply it by 2 right away. Get plus minus 25,758 0.59773. This is money, so I'm gonna round this to 2 decimal places. So 92,172 plus minus 25,758.60. Dollars. Oh, I guess I should do that math. 92,172 minus 25,758.60. Might need you to check, but I get 66,413.40 up to 92,172 plus 25,758.6 up to 117,930.60. That math is not difficult, right? That's not the hard part. We know that interpreting the interval, that's the hard part. Right? And so it's half the marks. So what do we have to do? Okay, I built a 95% confidence interval. So I'm 95% confident that whatever I built an interval around, that the average debt of these companies at the time of filing, right, is within this interval. So we are 95% confident the interval from 66,413.40 to 117,930.60 captures copy. I'm doing this so that I can write less, but also to highlight that you really just snag it from the question, right? Captures the average debt of these companies at the time of filing. If you want to emphasize that you're trying to capture the population mean, you could do something like the true average debt or the population average debt, but you don't have to. Okay. All right. Any questions about that one? I didn't prepare any more examples. I'm sure I could dig some up, but I don't know what to do. Wouldn't it be so nice of me to let you go early? But I want to cram your brains with more things. No, that's rude. I won't do that. Okay. So I'll post a video for Tuesday. You'll watch and enjoy the video. As far as I tell you to go on Moodle, I still haven't decided. Maybe it's just paired data, which, spoiler alert. Okay, I'll do a little spoiler alert. We can move into 2 samples, but for means, we're going to be able to deal with the special case where I have a sample, 2 samples, 2 measurements on the same subject. So a before and after score, for example, right? The same individual wrote a test before and then after studying or something, right? They ran a kilometer before they trained, and then they run a kilometer after, kind of before after studies. Those are paired, right? They're paired on the runner, for example, someone who's generally fast will start fast, end faster, hopefully, right? And someone who's generally slow would start slow and end faster, but still slower than, you know, their peers. And so paired data can handle that. But the spoiler is all you do is you take the difference. So you subtract one from the other, and now you have one sample means of the differences. And then you're just in a one sample mean type of situation, just like we were today. There, you hardly even need to learn it. You already know it. But I'll post the video, and I hope you have a wonderful long weekend. And I'll see you on Thursday next week.